I'm Dr. D.K. Tripathi, an assistant professor of physics under the Department of Basic Science and Humanities. So, since three classes, we are learning the statistical mechanics, and this is the fourth lecture which I want to deliver now. In the last class, we have seen that what are the assumptions of all three statistics, and we also come to know that what are the properties of bosons, fermions, and bosons. So today we will discuss the Fermi-Dirac statistics. So for this, let us suppose an ensemble which is having total capital N number of particles, and the energy of that ensemble is capital E. Now, if you recall the first class, in the first class I told you that particles are never to be put in the energy levels directly. Rather than that, they are put in the energy states. So if we consider that there are energy levels E1, E2, E3, E4, E5, EI, then other levels, and let us take that last level is nth level, En. So En. Now, let us suppose that this energy level E1 is having G1 number of energy states. This energy level E2 is having the G2 number of energy states, and so on. If energy level EI, that is test level energy, is if having the energy states GI number of energy states. Now we should know that what is test level. The test level is the level of which we will test the occupancy. Then like that, if we suppose that En, that is nth energy level, is having Gn number of energy states. Also, let's suppose that N1 number of particles are filled in G1 states of energy level E1, N2 number of particles are filled in G2 states of energy level E2, N3 number of particles are filled in G3 states of energy level E3. Like that, if Ni number of particles are filled in Gi energy states of energy level Ei. If this is like that, if um, n number of particles are filled in Gn states of energy level E1, then the thermodynamical probability of occupancy of the test level, that is ith level. You just recall that this is the customary to take the test level as the ith level. So here also we have taken ith level as the test level, and I'm saying you that we want to find out the thermodynamical probability of occupancy of the test level. So what it will be? It will be given by this Wi. Wi is equal to factorial Gi by factorial Ni into Gi minus Ni factorial. This will be the thermodynamical probability of distribution of N1, N2, N3 up to Nn particles in energy states of G1, G2, G3, Gi up to Gn states of energy levels respectively E1, E2, E3 up to En. Okay, now if this is, then um, this is for the test level. So if we want to find out that number of ways in which N2 number of or N1 number of particles are filled in G1 states of energy level E1. So this I will be replaced by W1 and by 1. So this will be W1 is equal to factorial G1 by factorial N1 into G1 minus N1 factorial. If you want to find out that number of ways or probability of thermodynamical probability of distribution of N2 number of particles in G2 energy states of energy level E2, then what it will be? I will be replaced by 2. So this will be W2 is equal to G2 by n2 factorial, g2 factorial by n2 factorial into g2 minus n2 factorial, like that. Now, if we want to find out the probability of occupancy of all these particles, n1, n2, n3, ni, and n, in energy states G1, G2, G3, Gi up to Gn. You see, G1 does not mean that one energy level. This G1 may have any value greater than 0. G2 may have any value greater than 0. N1 may have any value greater than 0. N2 may have any value greater than 0. So what we are saying, that if we want to find out that what is the thermodynamical probability of distribution of N1 particles in G1 cells of energy level E1, N2 number of particles in G2 cells of energy level E2, N3 particles in G3 cells of energy level E3, like that for all the particles, that will be multiplication of probabilities of all of these. That means W can be written as W1 into W2 into W3 up to Wn. Now, this pi sign, actually this is not pi, this sign represents the product of all the probabilities. So gi factorial by ni factorial into gi minus ni factorial. So this will be the thermodynamical probability of distribution of all these number of particles in all these number of energy states of all these energy levels. Okay. Now, if we go ahead like this, then by taking the Stirling's formula and just expansion of this will give us this relation. This relation is called as Fermi-Dirac distribution function. The derivation of this is not in your syllabus, that is why I'm not deriving, but it is very simple. Now you see, we have started with the thermodynamical probability, so that is why there is probability. So in the left side, there is probability. And what are these? Let us try to find out. This FEI, EI was the test level. So FEI represents the occupancy of the test level EI. The probability of occupancy of the test level is given by FEI. Okay, this is also called as Fermi function, is equal to 1 by e to the power ei minus ef by kt plus 1. Ei is the test level energy, ef is the Fermi energy. What is Fermi energy? This is the energy, reference energy level. K is Boltzmann constant and T is the temperature. This is plus 1. Now, what is reference temperature? You see, if that in that very ensemble E1, E2, E3, E4, E5 up to En energy levels are there, and we want to find out that to which extent this test level is filled up. So what we will have to do, if we want to estimate something, we require the reference with respect to which we will measure the occupancy of the test level. So that level which is taken as the reference energy level with respect to whom the occupancy of the test level is decided is called as reference energy level. And this reference energy level is named as Fermi energy level. Now you see how many variables are there. Here this energy difference is variable and this temperature is variable. K is constant thing. So there are two variables here. Energy difference. What will be this energy difference? If we are taking the test level and just below to it as the reference energy level, or just above to it as the reference energy level. So the difference between two consecutive energy level is one photon energy, that is h nu, or one photon energy. So that will be, if one photon energy, then this will be very small. Why? Because the difference between two energy level is one photon energy. Delta E is equal to h nu. The value of h is very small. 6.6 into 10 power minus 34 joule second. So because of that, this quantity h nu will be very small. So this will be very small. Okay, so let us take this EI minus EF as delta, and temperature is there. So if we want to find out the probability of occupancy of the test level EI, then that will be decided by two factors. First, the energy difference, and second, the temperature. So there are two variables, and because of that, there will be two cases which will arise. We, in the first case, we will have to vary the energy difference by keeping temperature constant. In the second case, we will keep the temperature constant by varying the energy difference. So what we conclude? We conclude that, you see, if we vary both of them, energy difference as well as temperature, then we will not be able to see that due to whom this occupancy of the test level is changing. So if we want to confirm ourselves that due to whom the energy level, you can say that occupancy of the test level is changing, for that you will have to vary one by keeping other constant. So because of that, there will be a rise of two cases. Okay, what will be the two cases? First case will be, you should not misunderstood it, that why I told you three cases, that three cases will arise. At first, I am explaining that how two cases will arise. You see, if we fix the temperature in the first case and try to vary the energy difference. Okay, so that will be the first case, case one. What should be the temperature? You see, I told you that if you want to see that due to the variation in the energy level, what is the change in the occupancy of the test level, then we will have to fix the temperature. So to which temperature we will have to fix? We will have to fix the temperature such that due to the temperature, there should not be any change in the occupancy of the test level. That means the particles should behave ideally due to the temperature. Temperature should not change. It should not alter the occupancy of the test level. So when it will happen? It will happen at the absolute zero. What is absolute zero? Absolute zero is the temperature at which the volume of the gas ceases. So because of that, at that point, that means at 0 Kelvin or absolute zero, the particle will behave ideally. So we are taking this temperature. So we are keeping the temperature constant as 0 Kelvin. And in the first case, if suppose this is EI and this one is EF. So what we are taking? We are taking that with respect to the just above level of the test level, to which extent this test level is filled up. What amount of particles are in the test level with respect to the reference energy level, and reference energy level is taken as the just above level. You see, you cannot say, or you cannot take any other energy level as the reference energy level. We will have to take the energy level from the same cluster of energy levels or from the same ensemble. So we are taking just above level as the reference energy level. Okay. So because of that, what will happen? FEI is equal to Ni by Gi. Ni by Gi is what? This Ni by Gi is the occupation index. Why? Because Ni is the number of particles in the ith level and Gi is the number of energy states. So number by number will give you index. If you put Gi equal to 1, what does this mean? That number of particles per unit energy state. In a single energy state, how many particles are there? So that will be called as particles density. That will be called as particles density, or we can call this as that to which extent the energy level is, energy state is filled up. If Gi equal to 1, so number of particles per unit energy state. That means to which extent the energy level is filled up. So this Ni by Gi is giving you the occupation, and it's a number, so that is why it is called as occupation index. Ni by Gi is known as occupation index. Now this will be equal to this one, Fermi-Dirac's formula plus 1. Now we have fixed the temperature to 0 Kelvin. If temperature is 0 Kelvin, then what will happen? Ei minus Ef. You see, Ei is less than Ef. And if Ei is less than Ef, then this will be negative quantity, negative delta by K into 0. Anything by 0, e to the power minus infinity. This will be e to the power minus infinity. What we can write? We can write it as 1 by e to the power infinity. And if it will be written as 1 by e to the power infinity, so 1 e to the power infinity is infinity. 1 by infinity, that is 0. 0 plus 1, 1. 1 by 1, 1. So we will get FEI is equal to 1. If FEI is equal to 1, what does this mean? The probability of occupancy of the test level is 1. That is maximum. The maximum value of probability is 1. So we have got that the probability of occupancy of the test level is 1. Why we are getting this? Because of the fact that from there Ni by Gi equal to 1. This means that Ni equal to Gi. What does this mean? This means that what number of energy states are there, that number of particles are available. And we know that this is Fermi-Dirac statistics. And in the assumption we have learned that there will be only one particle in each energy state. So what number of energy states are there? If that number of particles are there, so each energy state will be filled with a single particle, and because of that all the energy states will be filled up. And if all the energy states will be filled up, then the probability of occupancy of the test level will be equal to 1. So from that we can define this reference energy level. This reference energy level, which is called as Fermi energy level, is the energy level. Because you see what will happen. If FEI equal to 1, that means the test level is completely filled up. And if the test level is completely filled up, then ground state 1, 2, E1, E2, E3, E4, like that, this is test level. So if test level is completely filled up, that means lower states are also filled up. So what we conclude? That right from the ground state up to this Fermi energy level or reference energy level, all the states are filled up. All the states are filled up. So what we conclude? We conclude that reference energy level or Fermi energy level can be defined as the energy level up to which all the states are completely filled up at a temperature or at absolute zero temperature, or at a temperature T equal to 0 Kelvin. So reference energy level is the Fermi energy level, and this can be defined as the energy level up to which all the states are completely filled up at absolute zero. Now here at T equal to 0 Kelvin, what we have taken? We have taken that this is the test level and just above that is the reference energy level. But why we cannot take the lower energy level? We may take. There is no bindings that you cannot take the lower energy level as the reference energy level. So if we take the reference in just lower to the test level as the reference energy level, and we want to find out that with respect to that level, to which extent the test level is filled up. So at T equal to 0 Kelvin, 2 cases will arise, and because of that there will be 3 cases. Okay, so at T equal to 0, when E1 is greater than EF, at that very time what will happen? You see, Ni by Gi is equal to 1 by, here what we are getting? We are getting E1 is greater than EF. So EI is greater than EF. So EI minus EF will be a positive quantity. Suppose EI minus EF is delta, so it will be plus delta by K into 0. Okay, so plus delta into K into 0, that means anything by 0. will be infinite. So e to the power infinite. 1 by e to the power infinite plus 1. E to the power infinite, that is infinite. Infinite plus 1, infinite. 1 by infinite, 0. So what we'll get? FEI is equal to 0. We will get FEI equal to 0. How? Because Ni by Gi will be equal to 0. Now, if Ni by Gi is equal to 0, this means that out of Ni by Gi, Ni and Gi, someone is non-zero. Because if both of them will be 0, then 0 by 0 will be indeterminate form. We cannot define. So as it is defined function, defined value 0. So this means that Ni by Gi will, Ni and Gi will never be 0. Both of them cannot be 0. That means certainly one of them are non-zero. So which will be non-zero? Gi, because if energy level exists, energy state must exist. Particle may be there, may not be there. So Gi will be non-zero. So what will be 0? Ni. So Ni equal to 0. Ni equal to 0 means there is no particle in the ith level. There is no particle in the ith level. And because of that, the probability of occupancy of the ith level or test level is 0. What we conclude? That if these are the energy levels E1, E2, E3, E4, E5, suppose this is the reference energy level and just above to it is the test level. So we are not getting any particle in the test level. This means that there will not be particle in other upper levels also. Because if test level is not filled up, then the level above it will not be filled up. So from that, we can define that reference energy EF, reference energy level EF is the energy level above which all the states are completely vacant at absolute zero temperature. Okay, so reference energy level or Fermi energy level can be defined as the energy level above which all the energy states are completely vacant at absolute zero temperature. Now the third case. We have seen, we have put T equal to 0 Kelvin. We have fixed the temperature T equal to 0. And we have found two cases there. Now, if we vary the temperature, if we vary this temperature by keeping this energy difference constant, then what we'll find? So we are varying the temperature greater than 0. It may be any temperature greater than 0 Kelvin. Okay, because particles will behave normally, or if temperature will be very high, then they will behave abnormally. So that is why we have kept the temperature greater than 0 Kelvin. And at that time, we cannot fix both of them. If we are fixing the if we are varying the temperature, then energy difference is to be fixed. How we will fix it? By keeping the energy test level as the reference energy level. You see what we did? We have taken, this is the reference energy level and this is the test level. Just above that level was taken as the reference energy level. With respect to that, we have checked the probability of occupancy of the test level. In the second case, what we did, we have taken just lower level as the test energy level and we have seen the probability of occupancy of the test level. But we don't know that the level with respect to which EF we are trying to find out the occupancy of that test level, is it filled up or not? To which extent it is filled up? That means we will have to make reference energy level as the test level to check its occupancy, to which extent this reference energy level is fixed. And when we want to know that, then we will have to fix this Fermi energy level or reference energy level as the test level, because we can check the occupancy of the test level only. So we are making this reference energy level as the test energy level. And in doing so, what we did, you see the formula. Formula is this one, EI equal to EF. So this will be 0. 0 by K into non-zero. So 0 by something non-zero, that will be certainly 0. So if that will be 0, you see, if that will be 0, e to the power 0 plus 1. So 1 by e to the power, anything power 0, 1. So 1 by 1 plus 1, 1 plus 1, 2, that is 1 by 2. So what we have got? Fe equal to 1 by 2. So from that, what we conclude? Ni by Gi equal to 1 by 2. So from that, Ni equal to Gi by 2. What does this mean? This means that number of particles in the test level is half of the energy states available. So due to that, half of the energy states will be filled up and other half will remain vacant. Due to that, the probability of occupancy of the test level will be half, which is itself the reference energy level. So from that also we can define the reference energy level. How? That reference energy level is the energy level which is half filled, at a temperature greater than 0 Kelvin. Okay, so at a temperature greater than 0 Kelvin. Now, if we want to find out if suppose we are taking the condition that at 0 Kelvin, what happens to the occupancy of the reference energy level? That is at T equal to 0 Kelvin, EI equal to EF. What will happen? Will you be able to find out this? No. Why? Because this will be 0 by 0 form, indeterminate form. And if it will be indeterminate form, we cannot say that what will happen. So we cannot calculate that at T is equal to 0, if E1 equal to EF, what will happen? Okay. So what will happen to that? We cannot say. So what we conclude? We conclude that so from that, what we can say? That reference energy level is the level which is half filled at a temperature greater than 0 Kelvin. Now, if we increase the temperature from, suppose earlier temperature was 1 Kelvin. If we further increase the temperature from 1 Kelvin to 100 Kelvin, then what will happen? The particles from the lower energy level will diffuse to the higher energy level. So because of that, what will happen? The energy level which was taken as the reference energy level, that will be completely filled. But at that time, this will not serve as the reference energy level or Fermi energy level. At that time, the energy level which will be half filled, that will work as the Fermi energy level. So Fermi energy level is a variable level. The level which is half filled at any temperature greater than 0 Kelvin will be called as the Fermi energy level. So from that, we can define the Fermi energy level as the Fermi energy level or reference energy level is the energy level up to which all the states are completely filled up, above which all the states are completely vacant at absolute zero temperature, and is itself half filled at any temperature greater than 0 Kelvin. So this is the complete definition of Fermi energy level. Now all these things what we have discussed, that can be shown by a graph in simple manner. So this is the graph we have plotted, the graph between Fermi function and Fermi energy. Now Fermi function is the probability function, so its maximum value will be 1. Okay, so 0 we have taken 0.51, and let us suppose that this is the energy level EF, reference energy level, and just after that the higher energy levels are there. Okay, so what we have got, that up to reference energy level all the states are completely filled up. So all these states are completely filled up. Up to this, the probability of occupancy is 1. But if temperature is greater than 0 Kelvin, okay, or what we can say that in the second condition we have got that in this condition, that above Fermi energy level, that means after this, all the states are completely vacant. That is why the line is in the x-axis, the y-axis becomes level off. There is nothing in the y-axis. Up to Fermi energy level, there is complete occupancy. And after this Fermi energy level, there is no particle. Now, if we further increase the temperature, this happens at T equal to 0 Kelvin. If we further increase the temperature from T to T1, then what will happen? The Fermi energy level becomes half. So half. And because of that, what we will get? That the occupancy of the Fermi energy level will be 50%. Fermi energy level will be 50% populated. So all these things are shown, or all the discussions are shown in this graph. Now next is classical limit of quantum statistics. Classical limit of quantum statistics means when these two statistics, that is Fermi-Dirac statistics and Bose-Einstein statistics. This is Fermi-Dirac statistics and this is Bose-Einstein statistics. FEI equal to Ni by Gi equal to 1 by e to the power Ei minus Ef by Kt plus 1. This is Fermi-Dirac statistics. And FEI is equal to Ni by Gi is equal to 1 by e to the power Ei minus Ef by Kt minus 1 is what? This is Bose-Einstein statistics. Here it is asked that when these two quantum statistics will behave like classical statistics, that is Maxwell-Boltzmann statistics. This is Maxwell-Boltzmann statistics. FEI is equal to Ni by Gi is equal to 1 by e to the power Ei minus Ef by Kt. Now let us try to find out the differences between them. You see, in the Fermi-Dirac statistics, there is plus 1. In the Bose-Einstein statistics, there is minus 1 and there is no 1. So what is our task? Our task is that when this plus 1 and minus 1 will become no 1. So when it will be possible? This 1 can be neglected if this term will be very high. So when the value of this term will be very high? At t equal to, if the value of t is very high, at that time the value of this whole function will be very high. So what we conclude? That at very high temperature, this will become very high. So 1 by very high plus 1, that is very high. Or plus 1 will not be there, 1 will be neglected. So 1 by very high, that means very low. So Ni by Gi, that is particles density, will become very low. So what we conclude? That when the particles density will be very low, that means very less number of particles are there, and temperature is very high, that means at very high temperature and very low particles density, these two statistics, these two quantum statistics, Fermi-Dirac and Bose-Einstein statistics, will lead to the classical statistics, that is Maxwell-Boltzmann statistics. This is called as classical limit of quantum statistics. These are the references. You must go through them for having the deep knowledge or knowledge in depth, rather than the, and also for better understanding of the topic. Now, thank you.